Yeah, it's sharing now.
Now it's sharing.
Yes.
All right. All right. Number one. Is it clear there?
Yeah, it's visible. Yes.
So for number one, the photons of a wavelength. So we are given the wavelength in nanometers are scattered from electrons that are at rest. If the photons scatter at 60-degree relative to the incident of the photons, calculate the Compton shift, the kinetic energy impacted to the recoiling electrons and the angle. All right, now let me open so that. All right, so if the Compton, as it is given here,
The screen is no longer sharing.
the screen is not sharing.
It was sharing now. I don't know what happened.
Right, let's see. How about now?
Still not sharing.
Anything?
Mm-mm.
But you can hear me.
Yes, I can hear you. It went back like when you started logging in. It was showing the picture only.
It was showing only the picture.
Mm. Your picture. I think it's your profile pic. The profile picture.
My network is
I don't know. Maybe should I go out and try to log in again?
yeah, yeah.
Should I do that? Is it fine?
Yeah.
Yeah, it's sharing now, Sam. Hello, Sam. Hello, Sam. Hello, Sam. Can you hear me? Hello, hello, hello.
Can you hear me now? I think my
Yeah,
mic was mute. My mic was muted. Ne?
yeah. I can hear you now, but now the problem is it went back again. The when I logged in, it was sharing. Now it went back. I don't know if it's network or something. Hmm?
How about now?
Yeah, now it's sharing.
All right. So saying first, so for one A of the Compton wave shift, must know the formula first. So the formula for the Compton wave shift given by, I'm going to write the formula for the Compton wave shift. Must know change in wavelength equals to lambda prime um, m n constant over m mass that speed of light 1 minus 4 the equation that we are given. And then the interpretation of the value. Like for example, lambda. Lambda, you know that is the initial wavelength of the photon. So whenever we talk of lambda, we are referring to the initial wavelength of the photon. So lambda, the initial wavelength. If I see lambda, so the initial wavelength of the photon. Wavelength of the lambda. Right. Then the lambda prime, which are referring to the lambda prime, is what we refer to as the scattered or the final wavelength. So we are talking of the scattered
Oh, final.
or the final, final, that will be the lambda final wavelength of the photon. And the photon is just what we refer to as packets of energy which are found in light. Right. Then now what left is for us now to substitute the equation. Remember what we said about the equation to mention earlier on. So this is the setup of our equation. And you must also know the value of the mass of the electron they will be given at the back of the question paper. In our case, it was given at the end here. Get the information sheet. The mass of the electron, the Planck constant, so everything is given. So the next step, now we are substituting into the equation. So this one is a method of just substituting. What are you given? So you are given information. So the given info, you are given information. That lambda is equal to 5 nanometers. In the nanometers, you convert them to meter, which is 5
times 10 to the power
of negative 1.
9.
Then your theta, what is the value of theta? The theta was given from the question. If you find the theta is coming from the question where we are given the value. So the theta, the angle. Yeah. So now 5 marks just to calculate and punch in your calculator. Give away now. So the Compton formula, like it is the change in wavelength, is always the final wavelength, which is the scattered wavelength of the photon minus the initial wavelength of the photon. Right. Then you punch in your value, which is h over the mass of the electron multiplied by the speed of light, which is bracket 1 minus cos theta. Then from here, we are now substituting the value. We know the Compton wavelength of the electron. That's the Compton wavelength of the electron, which means h, the constant, and also the mass of an electron, also a constant. And c is a constant, which is given by 2,43 times 10 to the power of negative 12 meters. But you don't have to memorize this given information sheet. Then from the which is h over m, m which is h over m. That's information which h over the Compton wavelength. All right, so we are having h, this is our h, then the mass of an electron, which means the mass of an electron multiplied by the speed of light. So here you can see that the mass of the electron was not given. The mass of the electron was not. So which means what they required you to take them was for you, in this case, the Compton wave shift. Since we are not given h over the mass of the electron times the speed of light, but h was given, then what is the mass of the electron? So now what is the mass of the electron?
Which electron is it, sir?
Any electron just because here on the question we are only given the wavelength, then also we are not given the mass of the electron, which is 9, 11 times 10 to the power of negative 31. So which means you must know well that the mass of an electron, ME, mass of an electron, is to 9, 11
times
by
10 to the power negative 31.
51 kilograms. So that in, on our question paper we were given H. H was given 10 constant. Then just say the H over the mass of that electron multiplied by the speed of light. That's where we are getting this value. So the Planck constant 6,63 times 10 power negative 30. You can also punch it to verify the answer. So 6,63 times 10 to the power negative 30. Then you are dividing it by mass of the electron. Is 9,11 times 10 to the power of negative 31 times speed of light 3 times 10 to the power 8 times the speed of light 3 times 10 to the power 8. What do you get? So you must be getting an answer which is equivalent to 10 of meters.
I'm still punching, sir.
Negative
2,425 times 10 to the power negative 12.
from our forward
425.
from our 425
Yeah.
because of the 25. When you round up to 2 decimals, the 5 gives the 2 a 1. And that's why it's 243 times 10 power negative 2.
Yeah.
That's how we found our HME. Because all these are constants. So whenever you find HME, then you see that this is constant which is equivalent to 2,43 times 10 power negative 2. And where did we find the values? The values we are just finding them from Planck constant given. But here it seems that you needed to know by head that the mass of an electron is 9 times 11 to the power negative 51. Although they gave you the Planck constant and then the speed of light also was not given, you must know that the speed of light is 3 times 10 to the power 8 meters per second. Okay,
Yeah.
so now we are going to substitute into our formula, which is all the values with h over mec 1 minus cos theta. With the method of now substituting, define the change in wavelength. So you indicate the change in wavelength is equal to 2,43, the one that you got, times 10 power of
Negative.
negative times 10 to the power of negative 12, bracket 1. What is cos 1 minus cos? Just punch everything. Calculate. Tell us what is the change.
1,213 times 10 to the power negative 12.
1,2 what?
Uh, let me double do it again. 1,215 times 10 to the power negative 12.
5 times 10 to the power negative 2. The unit being converted to meter, not to we are no longer using meter. Alright. So that is the Compton wave shift. So why is it the Compton wave shift? Because they've used the Compton formula. So by using this Compton formula, we are calculating the Compton wave shift. This is the Compton formula, so which means we are calculating Compton wave shift given wavelength, and then we've been given also the degree theta. So we use all the values that to find what we have to find, which is the Compton wave. So the initial wavelength, photons of wavelength, we are using the initial wavelength. We have everything. Any question? Number 1. A.
No question.
So for 1B, talking of kinetic. So for 1B, talking of kinetic energy. So the kinetic energy imparted to recoiling electron. So also another formula that you use, kinetic energy. That formula for kinetic energy to recoil electron, K, are waiting for number 1. So the kinetic energy, K, kinetic energy, is equal to the Planck constant multiplied by the speed of light. 1 over the initial wavelength minus 1 over the final wavelength. So the prime is getting the final wavelength. Clear? Right. Then, what is the value of Hc? Hc in terms of electron volt. So you check on your question paper you given on the information sheet. Hc, I think I said it. Hc was not given. Hc was not given. So this value already you must know it by it. So we are applying the Planck constant, and even if you forget, this is how you do it. Even if you are given the Planck constant, what is the
Yeah.
Planck constant? What is the
Six
Planck constant?
6,63 times 10 to the power negative 34.
So you do it like this. So we are looking for Hc. Say you Hc equal to comma times 10 to the power of negative 34. Then what? These are joules. Remember the unit. These are joules multiplied by the second. So we are multiplying by the second.
3,10 times to the power 8.
multiply by 3 times 10 to the power 8. And the units are meter per second. So multiplied by second to the power negative 1 meters per second. So that the second, this second, which is cancels f times f to the power negative 1 exponent, the 1, f to the power 0, just like f multiplied by f to the power negative 1. F to the power 1 multiplied with f the exponent, which is f to the power 1 minus 1, which is equal to the second power 0 is equal to just 1. So seconds are gone. Now the unit which I'm left with is joules multiplied by the meter. So let's calculate what is the HC that we are using. 6,6 times 10 to the power negative 34 times 3 times 10 to the power 8. So which means this is 6,3 times 10 to the power negative 2 times 3 times 10 to the power 8. And then your units are now those. So what are you getting?
1,989 times 10 to the power negative 25.
1,989
989 times
times
10 to
10
the power negative 25.
is joules multiplied by the unit. So you want to find the HC in electron volt. So you go to your information sheet telling you this is conversion. So sometimes if they want to make it easy, they give you that the value of HC equals to what? In electron volt. So they tell you the answer of the electron. But here they split it up, which means you have to calculate yourself. So you know that 1 electron volt is what? 1 electron volt is 1,6 times 10 to the power negative 19. So if I want to convert now to electron volt, which means I divide by 1,6 times 10 to the power negative 19, that number, which I already calculated. So let's divide to convert to electron volt. So this HC, say HC equals to 1,989 times 10 to the power of negative 25 by dividing by 1,6 times 10 to the power of negative 19. We are now converting to electron volt. Why electron volt? Oh, 1 electron volt. 1 electron volt equals to 1,6 times 10 power joule. So which means this one to be joule. Here is 1 electron volt. So we are multiplying by every 1 electron volt, equivalent to 1,6 times 10 to the power 19 volt. Then at the same time, don't forget the unit which we're already sitting on the numerator, which is the joules and the meter. So it is the joules and the meter, they will stay already in the numerator. And then the units which are now cancelling, then you identify the units which are now cancelling, the joules and the joules, they are cancelling. Now we are left with the electron volt. And remember, this is just 1 electron volt equivalent. So let's what is 1,989 divided by 9, 1,6 times 10 power negative 9?
It's 1,243 times 10 to the power negative 6.
So HC equals to 1,243
times 10 to the power negative 6.
10 power negative 6. These are electron volt meters. So this is electron volt now convert this to nanometer. So HC in nanometer, how many? We want to use the electron volt nano. So what do I do to this one for me to put it in nanometer? Do I have to divide by what? Nanometers
So,
multiplied
say I have a question. For
by
us to convert into electron volts, is it required from the question, or is it a way to, if we want to find the nanometers, did the question say we must find in nanometers? Uh,
no,
in
there are
volt?
two ways of doing it. There are two ways of doing it. You can, the question, they can say calculate your answer in electron volts, or calculate your answer in what? In joules.
Nanometer, electron volts.
So there are two ways. So which means you can give your answer in joules, you can also give your answer in electron. So we are just doing both of them. For now, we are doing electron volts. Then we also find the answer in what? Joules. So that when the question comes, then it's specific. You use the method that you want, or the
Oh,
method that is. But if they don't specify the energy, just use joules or electron volt. But there won't be any, because sometimes it depends on the information that you are given on the information sheet. But if you are given in joules in the information sheet and you are not given electron volt, there is no need for us to use this method that I'm using.
okay.
You understand?
Yeah. So I must also check the formula sheet if it's provided.
And also, if the question does not specify to say your answer, your energy must be in joules or your energy must be in electron volt, then means you choose what you want, whether you want to put your final answer in electron volt or you want to put your final answer in what? So, like in this case, you choose what you want. There is no any restriction. Choose what you
Okay.
want. So that is our HC. Then in electron volt, so how do you convert these to electron volt?
Do you multiply by 10 to the power negative 9? I'm not sure.
Remember, a nanometer is it. Remember, when you want to convert nanometers, you divide by, they are dividing by, they are dividing this number. Converting to nanometer, they are dividing by 10. 1 times 10 to the power of negative 9 is now. Because nanometer, so this will be meter. It means here they are multiplying by 1 nanometer. 1 nanometer, like this. They are telling us that 1 nanometer is equivalent to 1 times 10 to the power negative 9. So which means the meter on the denominator will cancel the meter there on the numerator.
Mm.
Then you have nano electron volt. Remember, it was electron volt meter. So now we want to convert to electron volt nanometer. Then also we are having, in other words, we are also going to multiply by 1, comma 2, 4, 3 times is already times 10 to power negative 6 electron volt meter. 10 to power negative electron volt meter. Electron volt. So that this meter is here on the denominator cancels the meter on the numerator. The units they cancel. That's why I'm putting that we can cancel. Then you are left with electron volt multiplied by the nanometer. Then, using your mathematics, if you are given electron volt, the simplest way remember when you divide by a negative 9, exponent, they say dividing by negative 9, which means 10 to the power minus minus when you're subtracting 9. So in other words, on the exponent there, if you check, we are having a positive. So it will be times 10 to the power negative minus, because they are dividing a negative exponent, which was negative 9. So at the end, it will be the same as 10 to the power 3. So in other words, when you convert electron volts to meters, the electron volt meters, nanometers, we are simply multiplying by that number by 10 to the power 10. But it's good to do that you don't make it. So in the end, our HC just 1, 243, 243 times 10 to the power 3. Then we have electron volt nanometer. So yeah, so this is what we wanted to achieve. And then you can also indicate that this is now electron volt nanometer. And your HC in joules, remember the HC in joules? What did we find in joules? HC in joules. And remember, this is H, joule per meter. Joule, it was the joules, and then second. Then the C is in meters of light, meters per second. That's why we go apply by the meter in terms of joule meter. So if you are having your HC in terms of joule meter, it's a problem. Why is it a problem? If you are having in terms of joule, yeah, but it's still fine. You can use the joule meter. You can still use the joule meter. Then you convert to joule. Because this you can't use it as a joule, as energy straight away. So then once you are here, then you substitute the formula. Let's substitute the electron volts first. Now we are substituting the electron volts. So which means your kinetic energy K, so you come and plug your value, which means K is equal to HC, is 1,241, say 43, and 10 power. And remember, these are electron volts. 1,4 times 10 to the power negative 3, 10 to the power 3 bracket. Then the formula says 1 over wavelength. And remember, all the units are now in nanometers. So there's no need of you converting that other nanometers. You are no longer converting because already your energy is in electron volts. So this wavelength, there's no need of you converting it to nanometers. Why? Because already you are now working in nanometers. So you have converted your HC to nanometers. So that value as well is in nanometers. So the trick to that question was relying on conversion. Once you miss a conversion, your answers are gone. So you must take note of that. So which means 1 over lambda initial, which means lambda is the initial one. And what was the initial lambda? 5 nanometers. Minus 1 over, what was the final lambda? Did you calculate the final lambda? Calculate the final lambda from the previous question. We found that our change in lambda, check, the change in lambda was what?
1,15 times to the power negative
12 meters, isn't it?
Mm.
So in terms of nanometers, how many nanometers are these ones? They change. How many nanometers? What do? You divide by what? 10 to the power negative 9. So just divide that number by 10 to the power negative 9, which is just dividing that number by 10 to the power negative 9.
Which number?
1,215 times 10 to the power negative 12 meter. If you want
Divide
to
by
by 10 to the power negative 9, the whole number you are dividing it by 10 to the power negative 9, so that we know what is the change in lambda in nanometers. We want to know what is the change in lambda in wavelength nanometer. What are you getting? Nanometer. 1,215 times 10 to the power negative 12 divided by 10 to the power negative 9. What are you getting?
I'm getting 1,215 times 10 to the power negative 3
So 1,125
times 10 to the power negative 3.
times 10 power negative. So which means this is the difference. How do you get change in lambda? Say the change in lambda, yes, is our equation. Get that change in lambda. Just got now. 1, comma 1. Said 1,215.
15 times 10 to the power negative 3.
is equal to lambda prime, which I'm looking for. I don't know. These are nanometers. But what is lambda? The initial lambda was 5 nanometers. So calculate for me the value of lambda prime. We make that lambda prime the final lambda, the target of the formula. Because the change in lambda, change in lambda, change in lambda. So which means if I move the 5 nanometers to the right, to the 5 plus. So which means if I want lambda, if I want the final wavelength which I must put here, is the one which I have calculated here, that lambda prime will be 5 nanometers plus 1,215 times 10 to the power 1 negative 3 nanometers. That is the answer. So to make your life easy is what you are supposed to substitute here on the lambda prime. Is what you are supposed to substitute here on the lambda prime. So which means in other words, to make the equation one thing, we are just saying the energy A K is equal to 1,243 times 10 to the power negative 1,243 times 10 to the positive 3 bracket 1 over 5, which was your lambda, plus 1 over the lambda times the final, which means 5 plus 1 times 10. But these ones are not whole numbers. Remember, the other one is an exponent. So you can use your calculator directly there. You just say 5 plus 1, 215 times 10 to the power negative. And this is being divided with the denominator. Then you have a big bracket which is closing everything. Then what do you get as your energy, final answer? And remember, this is in electron volt. Electron volt. What is the energy? What energy are you getting? So, right. So you must verify the answer 0,0603 electron volt.
Let me do that one.
Verify that.
One, I got 0,200. I'm not sure.
Yeah. Check where you made it. The correct answer is everything we have sorted.
The first one where it says k equals to 1,24. Isn't it supposed to be negative? Oh no, I used the 1 comma something twice. 1,215.
But that's the correct answer. That is not working out. And tomorrow we'll show you where how we are going to calculate this kinetic energy.
Yeah, it says this one is long.
Yeah, it's 5 marks. Where is the mark?
This one was fast and easy.
All right, my if you continue tomorrow from here.
Okay, sir. No problem. Bye.